these are different combinations of transformations. For example, what does this do to the original graph? That's the graph of f of x, and we want to create a function g that first step f of x minus 1, and then subtract 1. What does this do when we change x into x minus 1? Say it again. Careful. Left will be negative 1 minus 1, which is not 0. Right 1. Yes, right 1. And then this one, what will it do? Exactly, down 1. Excellent. What about this one, which we haven't discussed? I would like to work on either this or this. We have not seen one like that. But let's also talk about this one. What does this do? First is the inside, and then is the outside. What does this do to graph of f of x? Excellent. This one is left 1. Now what about this? What will 1/2 outside do? Vertical shrinking by a factor of 1/2. Excellent. Is that clear? Questions? Okay, so let's choose either, I'm assuming this is 51. No, is this 49? 49 or 50. So I can illustrate the last transformation that I have not had. We want to look at 50? So 1/2 f of twice x. Perfect. I'm going to copy quickly this graph so we have it, because that's what we have to work with, and take it from there. Okay, so here's the graph. And this is problem 50 on page 295. And we have the point -4, -2. Oops, I didn't mean that. I meant this. We have -2, 0. We have 2, 0. We have -2, 0. We have 0, 2. We have 2, 2. And we have 4, 0. So here's the graph. So this is 4, 0. This is 0, 2, and this is -2, 0. And this is the graph of f of x. The problem is asking us to graph 1/2 f of twice x. So this is a new function that we want to graph using the graph of f of x, of course. So which transformation we have to present first? Because obviously there are, how many transformations we see here? Exactly. We see this change from f of x to f of twice x. That's the first one. And then we see 1/2 outside. So the first transformation will be f of twice x. And the second transformation will be 1/2 f of twice x. Okay. So what does f of twice x do to the original graph?
Horizontal.
Excellent. Horizontal shrinking by a factor of 1/2. 1/2. Okay, so let's start with this point. We are only addressing the x coordinates. We are not changing anything on the y. We are just changing the x coordinates. So the x coordinate of the first point I see is at -4. Where will this point move? Exactly. We are dividing its x coordinate by 2. This point, the second one in line, is at has x equals -2. Where will it move? That's it. This point is the next in line, 0, 2, has its x 0. Where will it move? Say it again. We are dividing 0 by 2. Where will it move? Nowhere. Excellent. The next point has x equals 2. Where will that point move? Exactly. 1, 2. And then we have a point that is 4, 0. Where will this point move? 2, 0. And this is the new graph. This graph is the graph of f of twice x. We changed x into twice x. We would have expected the graph to stretch horizontally, but it's exactly the opposite. It's the only one that is exactly the opposite. Everything else is, as we discussed, kind of, I would say, straightforward. Okay, so now 1/2 times f of twice x. Now this is the graph that we work with, f of twice x. What are we going to do to this graph? This time we change the x-coordinates or the y-coordinates? The y-coordinates. Very good. So now the y-coordinate of this first point is -2. So where will that point go? That's it. So its x-coordinate does not change, but its y-coordinate is halved. Very good. The next point has y equals 0. Where will it move? Nowhere. Very good. Awesome. The next point has y equals 2. Where will it move? Very good. Awesome. Next point has y equals 2. Where will it move? Good. And the next point has y equals 0. Where will it move? Nowhere. Excellent. So this is the graph of the final function, this one. This is 1/2 f of twice x. Any questions? This is how we address horizontal stretching and shrinking. Just a quick example now. I'm going to copy the same graph and just ask you a quick question. Same points, everything's the same. Everything the same. Same graph. And let's say now we want to graph f of 1/2 x. What am I changing now? Am I changing x or I'm changing y? I'm changing x. Very good. What do I do? This has x coordinate -4. Where will it move? Exactly, -8. Because I have to multiply it. Here I divide it. Its x coordinate was -4. I divided by 2 because I had 2 in front of x. Here I have 1/2 in front of x. Is the opposite that you would expect. If this is -4, it will move exactly where x is -8. That's why I wanted to give you another example. The coordinate of x here is -2. The x coordinate of this point is -2. Where will it go? Very good. The x coordinate of this point is 0. Where will it move? Nowhere. Very good. The x coordinate of this point is 2. Where will it move? Good. Excellent. And this coordinate is this point has x coordinate 4. Where will it move? Perfect. Excellent. So this is the graph of f 1/2 x. Exactly the opposite as I would, if you want, would have expected. If we change x into 1/2 x, we multiply all x values by 2. If we change x into 2x, we divide, or you can say you multiply all x coordinates by 1/2. Or we divide all x coordinates by 2. Questions? Of course, if I put something else in front, if I put a minus now, then I'm going to reflect the graph. Let's also do that if you'd like. So -1/2 x. This y coordinate moves up here. This y coordinate doesn't go anywhere. This y coordinate will move the opposite. The same one here, the opposite, and this one doesn't change. So this graph, this one, is the graph of negative f of 1/2 x. because it has an extra transformation. It has a minus in front. And of course, we can go on forever. We can add, subtract. We can change a lot more here. Okay. So our next section is 2.6. I don't think there are any news in 2.6 for you. I think this is going to be entire review, but I'm going to go over everything. I call it Algebra Functions. In addition, or and, I would say, function composition. I know you're going to ask why we need it, and I'll give you examples after we discuss it, of course. So algebra functions, we just add, subtract, multiply, and divide functions. That's what algebra functions means, right? We are adding, this time subtracting, multiplying, or dividing functions. So given, let's say, f of x and also g of x, I have two functions. I may have more than two functions, but let's suppose I have only two functions. What do you think this represents? And then this. And then this. And then this. This is read f plus g of x, f minus g of x, f g of x, f over g of x. Exactly these operations that we just mentioned. So what do you think the first one will be? What does it mean? What? Of course, just common sense. So let's write all of them. Just go ahead and write them. It's a lot of writing in this section. A lot of writing, but that's okay. I didn't mean that. This is this. I jumped ahead. I'm going to erase it. Of course, this is f of x times g of x. It has nothing to do with the ratio. Okay, notice that on these first three ones, I did not write if. But I wrote if on the last one. Why did I write if on the last one? And what's with that if? We know this. We looked at rational equations.
G can't be 0.
Of course. G indeed cannot be 0. We know that. Whenever the denominator of a fraction is 0, the fraction is undefined. So that's not allowed. Although I did not write if on the other ones, right? Because I'm adding, subtracting, multiplying, and dividing. Before we pick an example, and if you'd like, just give me two functions, any two functions that you can think of. A linear, quadratic, any function you want. Rational?
2x,
No.
2x plus 4.
This one or this one, doesn't matter. Okay, 2x plus 4.
X plus 4.
Okay, let's say x squared minus 4x plus 7. Okay, so this is what type of function? Quadratic, and this one is? Okay, everyone knows that for sure. Good. Okay. Make up your mind, son. In or out? Okay, so before we even talk about determining, I would like to determine all these functions. Given these two, we can create new functions. Given two functions, we can create functions by adding, subtracting, multiplying, and dividing them. But I want to give you an example because this is very important. And let's look at two graphs. A graph of a function f. Let's say, I'm just making stuff up now. So let's say this is function f of x defined, let's say, between -10 and 2. And let's suppose I have function g. Let's say it's defined between -2 and 20. And I'm going to ask you to determine fg at 4. You will say that's a piece of cake. Fg at 4 means f of 4 times g of 4. That's not a big deal. And you will say it's f of 4 times g of 4. But what is the problem? Is there a problem?
Yeah,
There is no
f of 4.
Exactly. F of 4 does not exist. Here is 4. If you draw a vertical line, you will clearly see it does not cross the function f. So f of 4 does not exist. Undefined. So in order to create these functions, the sum, difference, product, and ratio, given two functions, what do they have to have? If they don't, there is no point in creating these functions because there is nothing I can plug in. So what do they have to have? They must have a common domain. If they don't have a common domain, then these functions mean nothing because there is no value that we can plug in them. You can create them, but there is no value that they exist for. So can anyone give us the domain of function f? Domain of f. Very good. Negative 10 to 2. Awesome. The domain of g to 20. Although these don't mean much, we really want the common domain. Can anyone give me the common domain? Exactly. So if I want you to determine f comma g of blah, 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 it has to be a number between negative 2 and 2. Because otherwise you will not be able to determine it. Because one or the other will not exist of the functions. So here is the important information the point I'm making here. I cannot create these functions unless they, f and g, have a common domain. Doesn't have to be negative 2 to 2. It can be anything. But if they don't have a common domain, then those functions don't exist. Because there is no number you can plug in them. Okay, so now we can go back. So remember the idea of the common domain when we add, subtract, multiply, and divide functions. Also, the common domain will always be the domain of the sum, the domain of the difference, and the domain of the product. Always. Notice that I did not mention anything about the ratio. I don't know. I don't know if the common domain will be the domain of the ratio as well. But we know for sure for any two functions, given functions, if they have a common domain, the common domain will always be the domain of the sum, difference, and product. Always. Okay, so now we have these two functions and we want to determine the sum, difference, product, and ratio. So I'm going to copy the functions here. So I have x squared minus 4x plus 7 and g of x equals 2x plus 4. And yes, we'll look at an example when we add, subtract, multiply, and divide functions in a minute. A word problem, an application. Okay, so we are asked to find all these functions, but I have to start with the domain of f, I have to continue with the domain of g, and I need to continue with the common domain. Because if I realize that there is no common domain, then there is no point in even bothering with these functions. They're not useful. A function is good as long as I can plug in numbers in it and get an outcome. But if I can't plug anything in, what's the use of that function? There is no use. Okay, ready? What is the domain of f? What is the domain of any polynomial function? Forever and always. Yes. Say it again. Negative infinity to infinity. Polynomial functions don't have restrictions. They don't have x in the denominator. There is no square root in there. And there is no log, which we will discuss in chapter 4. So these, you can plug in any number. Give me any number, 15. I'll plug it in and give you a number back. -3, I'll plug it in and give you a number back. It continues forever. So polynomial functions, we wrote that. I think we wrote it some time ago. I'll write it again if you want. Polynomial functions. We need it in chapter 3 anyway. Are defined on negative infinity to infinity. They are defined on all real numbers forever, always. Okay, so then what is the common domain? If the domain of f is this and the domain of g is that, what is the common domain? Which is also the domain of the sum, the domain of the sum, the domain of the difference, and the domain of the product, as we wrote it here. Same thing. Okay, so let's determine the sum. I know there is a lot of writing here, so please keep up with me. It's not difficult, it's just writing f plus g again. I copy f of x, which is x squared minus 4x plus 7. I copy 2x plus 4. I combine like terms, x squared minus 2x plus 11. So this is a new function determined by adding the two initial functions, f and g. We can continue with the difference. We're just combining like terms. There is really nothing. Let me know if you have questions, please, anything. So f minus g. So this is nothing else but f of x minus g of x. I copy f of x. But remember, I have to put parentheses and minus in front of 2x plus 4. Because now I have to distribute. So this is x squared minus 4x plus 7 and minus 2x minus 4. As I said, nothing difficult here. I just have to write a lot. So this is x squared minus 6x and plus 3. And this is a new function. Was obtained by subtracting g of x from f of x, or f of x minus g of x. Same idea with the product. Again, a lot of writing. F of x multiplied by g of x. I copy them side by side and I distribute. Nothing difficult here. It's all the same algebra that we know from different courses. I will distribute 2x to these three terms, and then I will distribute 4 to these three terms and combine like terms. You don't have to use the same method. You can distribute from here, but it's easier for me to distribute 2 terms than distribute 3 terms. I may forget the last one. Who knows? You don't have to change your method. Use the method you like. So I have 2x cubed and minus 8x squared and plus 14x and plus 4x squared and minus 16x and plus 28. I just distributed 2x and then 4 respectively. And now I combine like terms, and I get 2x cubed, and then minus 4x squared, and then minus 12x, and then plus 28. What does this represent? A new function. How was it obtained? Multiplying f by g. All these functions, sum, difference, and product, have the same domain, which is common domain, all real numbers. Finally, I got to the ratio. The ratio is f over g, which again by definition is f of x over g of x. I copy the numerator as x squared minus 4x plus 7. And then I copy the denominator as 2x plus 4. But I have to put a comma and a big if. If what? And we discussed this a long time ago. Actually, after linear equations, the second thing we did this semester was rational equations. And that's the reason why I asked you, please remember restrictions, because it makes our life easier now when we talk about functions. -2 indeed. X cannot equal -2. So therefore, the domain of this function is just for the ratio. The domain of the ratio is
-2
yes,
to -2.
Yes? Union
-2.
to infinity. That's it. As you see from the common domain, which was all real numbers, I had to remove -2. Why? Because 2x plus 4 equals 0, as we've done more than a month ago, x does not equal -2. If you have any doubts, please tell me and I'll show whatever you need me to show. I don't want you to feel that I'm skipping steps. I'm just saying that this was discussed many times, and I'll do it again if it needs to be done. Is it clear why we get x not equal -2? Yes? Is it yes or no? Okay. 2x plus 4 cannot equal 0. 2x cannot equal -4. X cannot equal -2. Is this better? The denominator, it's a rational function. The denominator cannot be 0. Is this okay, everyone? Yes? Okay, perfect. Now let's talk about the fifth method. The fifth method of creating new functions. That is called function composition. It's a totally different method. It's not addition, it's not subtraction, it's not multiplication, it's not division. Okay? The notation is f, a little circle, and g of x. Or g, a little circle, f of x. Of course, this is not the way we read it. So here's how we read it. F comp g. F comp g. Or in this case, g comp f. I didn't mean to put it there. So you can also read it the composite of f and g. If you don't like f comp g, you can say the composite of f and g. If you don't like g comp f, you can say the composite of g and f. But what does this mean, really? It's a fancy notation. I hope you agree. But what does it mean? So here's what it means. We're talking about f comp g first. 3 bubbles. G is the first function. It's called the inner. And f is the second function. It's called the outer. And you can say this is not what I see. I see f as being the first and g being the second. True. But when you apply it to x, this really means f of g of x, which makes g of x closest to x. G is closest to x. G of x is the inner. And when you are done with this number, then you are applying the outer function, which is f. So then, x, again, which is the first function, go, very good. So I get g of x. And then to g of x, I apply which function to get this? F of g of x, indeed. I will not test you on finding the domain of the function composition, but I would like to show you what the problem could be. So what was the problem here? What was the problem that we could have run into for adding, subtracting, multiplying, and dividing? What could the problem be? That the two functions do not have exactly. If the two functions do not have a common domain, it's useless to even think of those functions. So that could be the problem here. However, for the function composition, it's not the same. They do not even have to have the same domain. Nobody cares whether they have a common domain or not. The story is totally different here. Here's the story. And again, I just want to show you what it means. I will not test you on this part. So there are problems in the book, but I truly believe this is part of pre-calc and calc, not of this class. So I'm not going to test you on this. But you may see this in my math lab, in my lab's math. So that's why I want to show you the idea. So G is applied to X. What does this set represent for G? The what for G, where we pick x values.
For the domain.
Excellent. This must be the domain of G. Agreed? That's where we pick x values for G. Perfect. Now please tell me, what is this set for G? This is its domain, and this is the values of G of x, or y values. So what could this set be for G? If this is its domain, of course. Excellent. This must be the range. So this is the range of G. Excellent. Stay with me. One more thought. Forget about this now. Please tell me, what does this set represent for F? This set.
The domain.
Of? Excellent. Well done. Great job. So this at the same time must be the domain of f of x. So what could go wrong? Here's what could go wrong. I apply G to 3. So let's say 3 through G gives G of 3 to be 10. So this is, I just picked a number. I said 3, I applied G to 3, and I get G of 3, and that number is 10. But now I have to apply f to 10. But if the function f of x is 1 over x minus 10, I'm going to say to you, plug in 10 and give me the answer. But you won't be able to. So the range of G contains 10, but the domain of f does not. So now these two sets, not the common domain, and the concept of common domain doesn't have any place here. These two have to overlap in here carefully. So whatever I bring as a value of G has to be applicable, or I should be able to apply f to. If not, the chain will be broken. That's all I would like you to remember, nothing else. So in this particular case, when we create function composition, the middle set, the range of G, and the domain of f have to work well together. If they don't, then the function composition cannot be created for those values. Nothing else. That's it. Okay, so of course, the idea is the same with G comp f. So this is f applied to x, f of x, and then g of x for this one. Just they are reversed. Okay, I'd like to see how the mechanism works. You gave me before two functions. I'm going to copy them from a few minutes ago because they are very good functions. You said g of x as 2x plus 4, and f of x as x squared minus 4x plus 7. I thought the cell phones were away in my class. I was hoping for that. Okay, so let's look at f comma g, which by definition is f of g of x, and also look at g comp f in a minute. So how do I start? So remember, the idea here is to first replace the inner function. You don't have to cross it out like that. I'm just making a point. So this function replaces g of x. 2x, this expression is g of x. So this is f of 2x plus 4. So now we go back to f because we need to analyze what f is telling us. What does f say? F says blah squared minus 4 times blah plus 7. But this is my blah now. This is my blah. So whatever squared minus 4 times whatever plus 7. We've done this before, even on the previous test. How was it called? Thank you. Because of f of x plus h. Pretty similar. Yes. Thank you, Alicia. Very good. Excellent. Good. So then please tell me, dictate, and I'll put it in.
2x plus 4 squared minus 4, 2x plus 4.
Excellent. Now you remember this is exactly what we did with the difference quotient. It's just that we did not replace the x by x plus h, but by 2x plus, in this case, by 2x plus 4. Okay, perfect. Next step. I need to simplify. I cannot leave it like this. So can anyone suggest the next step? By the order of operations, we need to. We cannot distribute by the order of operations. However, I have to say that yes, you can square this and at the same time distribute. You could. But distributing or the product is not our first priority. But yes, you can do it at the same step. I agree. If that's what you meant, Chris, I agree. Okay, so then, yes, how many terms do we get? Please make me proud. 3 terms, very good. First day of classes, please review those formulas. Please, I'm begging you. I'm begging you, please review. Okay, so what will you write? 4x squared plus 2 times, very good. 16x plus 16. Awesome, thank you. Bernie, right? Bernie was giving me the answer? Or somebody else? Who do I thank to? Okay, I thank everyone then. So minus 8x minus 16 and plus 7. Whoever said it, I'm very happy. Okay, so then this is 4x squared, and then plus 8x, and then plus 7. So this is a totally new function created by function composition, f of g of x. Normally we are asked to determine both. The other direction. Let's determine the other direction as well. Any questions on this problem? Please, anything. Any questions? The other one, can anyone dictate? How do I write this one? Excellent. Very good. G of f of x. And now I replace this. And this is it. So I have g of x squared minus 4x plus 7. Okay, so then what? I look at g. G says g of whatever is 2 times whatever plus 4. 2 times whatever plus 4. So please tell me what to write. Yes, excellent. Excellent. Right. Great job. And plus 4. That's it. Much easier. I don't have to square because this is a linear function. Excellent. So I just distribute 2x squared minus 8x and plus 14 and plus 4 will be 18. I'm lazy. I didn't want to write it twice. I'm kidding. You know what I mean. It's 14 plus 4. Is this a little blurry or I need new glasses? Okay. Questions on this? Questions? Okay. I would like us to look at an application and also read from a graph. So let's read from a graph first. Let me